In this presentation, I'm going to explain the previous GATE questions and answers for the year 2024. And the topic covered is analog electronics. Now let us see the first question of 2024 GATE question. That is, in the given circuit, the diodes are ideal. The current I through the diode D1 in milliamperes. That is rounded off to 2 decimal places. Therefore, we have to calculate what is the current through diode D1, that is in milliamperes. Now, this circuit can be reduced to the equivalent circuit like that when both say diode D1 and D2 are conducting. And this is the equivalent circuit when D1 and D2 are conducting. Now, the question is that what is the current through the diode D1? Now, coming to this circuit, equivalent circuit here, applying this point at this node, applying the, of course, if you write the nodal equation at this point, like Vx is the voltage at this point. For Vx minus 10 volt is there, minus 10 divided by 1k, that is this current was this. Then plus Vx divided by 1k, that is this current, plus Vx minus 3 volt, because here 3 volt is connected here. Vx minus 3 divided by 1k, that should be equal to 0. Actually, we are applying the based on the Kirchhoff's current law, the nodal equation is written, and from this one unknown is Vx. Therefore, 3 Vx minus 13 divided by 1 kilo ohm equal to 0, or Vx equal to 13 by 3 or 4.33 volts. For the voltage at this point equal to 4.33 volts. Now the question is to find out this current, that is noted as the current ID1. Now, here, this voltage here is equal to 3 volts. Therefore, this resistance equal to 1 kilo ohm. Therefore, this current equal to 3 divided by 1 kilo ohm, which is equal to 3 milliamperes. Therefore, that is noted as the current I2. So, the I2 equal to 3 volts divided by 1 kilo ohm or 3 milliamperes. Now, we are applying the Kirchhoff's current law to this node as such. Here, I1, that is, here this is equal to I1 plus ID1, that should be equal to I2, this current, which is equal to 3 milliamperes. Therefore, I1 equal to Vx minus 3 volts divided by 1 kilo ohm, that is 4.33 volts minus 3 volts divided by 1 kilo ohm, plus this current ID1, that should be equal to 3 milliamperes. Now, substituting this one, we'll be getting ID1 equal to, that is equal to 3 milliampere minus this one equal to 1.33 milliampere, or that's equal to 1.67 milliamperes. So the current through the diode D1 equal to 1.67 milliampere. Now let us see the second question, that is 2024 GATE question, in which a biasing circuit is shown in the figure. This is the biasing circuit, voltage divider biasing, in which here VB is given as 0.7, this voltage equal to 0.7, and beta value, current gain is given as beta value, common emitter current gain, which is equal to 100, and Q point or quiescent point values of VCE and ICR respectively. What are the values of VCE and ICE at the quiescent, VCEQ and ICEQ, that is to be calculated. Now this is a voltage divider biasing, in which if you draw the corresponding Thevenin's equivalent circuit at the input side, it will become VTH and RTH. Or if you take what is the voltage coming at this point, which is equal to, that is 12 volts, that is 12 volts divided by 50 plus 100 into 50, that is 12 into 12 divided by 150 kilo ohm into 50. Therefore, that is equal to 4 volts. Therefore, the voltage coming at this point is taken as the VTH, Thevenin's equivalent voltage, and corresponding resistance RTH is given by these two will be in parallel. Therefore, 100 and 50 kilo ohms are in parallel. 100 into 50 divided by 100 plus 50 or 33.33 kilo ohms. Therefore, this is the equivalent circuit from the input side. There's a VTH which is equal to 4 volts and the RTH equal to 33.33 kilo ohms. And now this is the input side. Now continuing the same problem. Here we have found out what is VTH and what is RTH. And here, RE, the RE resistance RE is given as 1 kilo ohm and corresponding IA. If this is the IB, is the base current, and IC equal to collector current, IC and IB, IC equal to beta times IB, so common emitter current gain, beta times IB, and the total current IE is equal to emitter current is equal to IB plus IC or IB plus beta times IB or 1 plus beta times IB. Therefore, the current through IE equal to 1 plus beta times IB. Now we are going to apply the Kirchhoff's voltage law, KVL, to this input loop. Applying KVL to the input loop, we'll be getting 4 volts, 4 minus the drop across this one equal to 33.33 kilo ohms into 10 raised to 3 into whatever the base current IB. Then this drop is given as 0.7 volt plus, this plus and minus, therefore it is equal to minus 0.7. Then drop across this one, again minus beta equal to 100, therefore 101 IB, 101 IB into this resistance equal to 1 kilo. That's equal to 0. Therefore, in this equation, the unknown is the base current. You can solve this equation and get the what is the base current. Therefore, base current equal to, will be deriving it is equal to 4 minus 0.7 divided by 134.33 into 10 raised to 3 or 24.56 microamperes. That is the base current. Now the collector current is given by beta times IB, which is equal to 100 into this current, 24.56 beta times IB, or which is equal to 2.46 milliamperes. Now we calculated what is the collector current and what is the base current. Now this, the collector current is the one of the Q point value of the current. This is the collector current at the quiescent point, that is calculated as 2.46 milliampere. Next, we have to calculate VCE. In order to calculate the VCE, we have to take the output loop. Therefore, we are applying KVL to the output loop. Now, applying Kirchhoff's voltage law to the output loop, the total voltage VCC, or that's equal to 12 volts. That VCC equal to the drop VCC equal to the drop across RC plus VCE plus drop across RE, or VCE equal to VCC minus the drop across RC, IC into RC minus the drop across RE, IE into RE. That is the drop across VCE, collector to emitter voltage. That can be obtained from the output loop. Or from this one, if substituting that one, 12 volts the VCC minus 2.46 into 10 raised to minus 3, that is the IC, into 2 into 10 raised to 3, that is the 2 kilo ohms, minus the drop across this one. And drop across means that IE equal to, calculated as IE equal to 1 plus beta IB, which is equal to 2.47. 2.47 into 10 raised to minus 3 into 1 kilo ohm, 1 into 10 raised to 3, which is equal to 4.6 volts. Therefore, the Q point is the quiescent point equal to VCE equal to 4.6 volt and IC equal to 2.46 milliamperes. Therefore, the answer option, if you see that one, answer option is the A. Option A is the answer. Now, let us the third problem, 2024 gate question. That is, a difference amplifier is shown in the figure. Assume the op amp to be ideal. The common mode rejection ratio in decibel of the difference amplifier is, that is to be rounded off to 2 decimal places. Therefore, this is the difference amplifier. It is asked to find out what is the common mode rejection ratio. Common mode rejection ratio is equal to the differential gain divided by the common mode gain. In dB, it is equal to 20 log AD by AC. We will see one by one. Here, this is the circuit that is redrawn like here. That is same thing. I'm marking it as this resistance. I'm putting it as R1. This is RF. This is R2, and this is to R3. Just for analysis purpose, I have put like this one. Now coming to that one, the voltage, output voltage is equal to, when output voltage means, first we have to consider when this voltage is present. That is when here V into is present. When V into is present, the voltage at this point, that is the non-inverting point, is given by V into divided by this resistance, that is R2 plus R3 into this R3, that is VI2 into R divided by R2 plus R3 into R3. That is the voltage at V plus this voltage. Therefore, that is a non-inverting amplifier. Therefore, the gain is equal to whatever this voltage into 1 plus RF by R1. That is into 1 plus RF by R1. Therefore, this is the voltage. Because of the voltage V into the voltage at the output is given by this is 1. Now again, as per the superposition theorem, what we are assuming, that's the second voltage is present. First we consider V into is present. At that time we just grounded this one, and we have seen the corresponding output voltage equal to this much. V into R3 divided by R2 plus R3 into 1 plus RF by R1. This is the voltage at the output when V into alone presents. We are grounding that point. Next step is that you are grounding this input V into, and we are assuming that V in 1 is present. Then it is just equivalent to a inverting amplifier, in which the output voltage equal to V0 equal to minus RF by R1 into V in 1. Minus RF by R1 into V in 1. Therefore, when the both sources are present, it is a summation of the two voltages as per the superposition theorem. Therefore, this is the output voltage equation here when V into as well as V in 1 are present. Now the V0 equal to V into, we are substituting these values of this is equal to R1, R2, R3 and RF. We are substituting in this equation, and we are getting it is equal to taking V in that one, this will be getting this equation. Now we are taking this V into as just for that V1 and V in 1 as capital V2. Therefore, this equation I am rewriting as one, rewriting this one as V into equal to V1 into this much plus this into V into equal to V2. Or this term, this is called the term A1, and this is term defined as A2, or A1 V1 plus A2 V2, where A1 is this much, and which is equal to, will be calculated, will be get 9.71. And this is equal to A2 V2, or this A2 equal to, will be getting, it is equal to minus 101 kilo ohm divided by 10.5 kilo ohm, or equal to minus 9.69 ohms. Therefore, we got what is A1 and what is A2 by comparing these two equations. This is the equation stating the output voltage in terms of V1 and V2. The generalized equation for the output voltage A1 V1 plus A2 V2. Comparing these two equations, we got what is A1, that is this is A1 and this is equal to A2. Now continuing the same problem to find out the CMRR, common mode rejection ratio. A1 we got it as 9.71, A2 we got it as minus 9.619. Now the common mode rejection ratio is given by differential gain divided by common mode gain, AD by AC, where differential gain is given by A1 minus A2 divided by 2, and common mode gain given by, that is under modulus of A1 minus A2 divided by 2, and common mode gain is given by modulus of A1 plus A2. Therefore, AD equal to, differential gain equal to A1 9.71 minus A2 equal to minus 9.69 minus 9.619 divided by 2, or it is equal to 9.6645. That is the differential gain. And common mode gain equal to A1 plus A2, or 9.71 minus 9.619, which is equal to 0.091. For the common mode gain equal to 0.091 and differential gain equal to 9.6645, meaning that difference in signal is amplified by this gain AD, and the common signal is being amplified by the gain 0.091. Therefore, the common mode rejection ratio is given by modulus of AD by AC. Modulus of that is 9.6645 divided by 0.091 equal to 106.2. That is the common mode rejection ratio. And in CMRR, common mode rejection ratio in decibel is given by 20 log AD by AC or 20 log 106.2, which is equal to 40.52 decibel. So the answer is for this circuit, the common mode rejection ratio in dB equal to 40.52 dB.